The broadcast is now starting. All attendees are in listen-only mode.
Welcome everyone to our first webinar of 2019. I'm Stacy Elliott with RioSense, and our first topic of the year is going to be talking about measuring the viscosity of polymers in solution. And based on some measurements that we recently have done, we want to emphasize all the value in really looking critically at your viscosity measurements and how this can help you when you're looking at your sample preparation procedure. So that's going to be the focus of today's discussion. And just a quick overview of what we're going to cover. We're going to review the viscosity basics, because that's important in this case, and then the VROC technology, which is the core technology of our instrumentation. And then we're going to get into the bulk of the discussion, which is going to be looking at polymer solutions, viscosity measurements of polymer solutions. And we're going to talk about the system we're working with, how we've prepped the samples, and then get into the viscosity data. And this is going to include shear rate dependence, and then because of some anomalies that we have seen in the data initially, we're going to go into a more detailed review of the data, specifically transient behavior. And that's going to become clear what that means as we get into it. And then ultimately, we're going to discuss concentration dependence of the viscosity for the polymer solutions and some analysis that you can do with models. And sort of, it was a little hard to lay this out exactly as we go through it, but we're also going to talk about the polymer dissolution process and how this is important when you're doing your sample prep and what it can mean when you are collecting your viscosity data. Okay, so starting off with just to remind you what viscosity is. Viscosity is going to characterize the resistance to flow, and it's a defined property that's ultimately calculated. So viscosity is shear stress over shear rate. So the easiest way to view this, we have a schematic here where we're looking at a fluid between two plates. The lower plate is stationary. We're moving the upper plate at a particular velocity. So this is going to generate a shear rate in the material, which will be defined as the velocity divided by the height of the fluid, or the distance between the plates. And then a shear stress is going to be required to move this fluid, which is going to be the force applied to the upper plate divided by the area of the fluid in contact with the plate. So viscosity is defined as stress divided by shear rate. And that means that the viscosity it's a calculated property. It is not directly measured. So what that means is that the calculation is only going to be truly valid if all of the assumptions of the calculations are met. And that also then leads to the fact that viscosity data can be heavily influenced by measurement artifacts. So it's always important to critically review your data and assess whether or not things are going as you expect them to. So hopefully as we go through the talk, you'll see what I mean about the importance of viscosity being a calculated property, not directly measured, which means if it's calculated, there are assumptions that make this calculation valid, and they must be met, or you're not going to be getting what you think you are. And measurement artifacts can occur in viscosity that can sort of lead you astray. But if you look critically at all of the information that's given to you from the measurement, then you can, understand what's going on and decide the quality of your data. So the technology, all of our measurements were done using our instrumentation, and our technology is the VROC technology, which stands for viscometer rheometer on a chip. And this is a combination of microfluidics and MEMS. So what we have then is a flow channel, microfluidic flow channel, and beneath the flow channel are 4 silicone pressure sensors. And so the way the calculation is done for our system is that we are controlling the flow rate through the channel, which we can then translate into a shear rate. We are measuring pressure drop across the flow channel, which we can then translate into a shear stress. So then we calculate viscosity as shear stress over shear rate. And I just wanted to point out here, I've put a plot of pressure versus sensor position. And this is basically then what we're measuring as the fluid is flowing through the microfluidic channel. And this is a situation where we have a fully developed, well-developed flow profile, uniform sample. Everything is going according to plan in this case. So what you have is this pressure drop across the channel. is linear with the R² value equal to or very, very close to 1. And we're going to revisit this pressure drop across the flow channel as we go through the talk, because this is where you can start seeing indications of some issues where things might be not as you expect them to be. And just to also point out, as I said before, that viscosity is calculated, not measured. So what we're really measuring here, although what we show you is pressure, what we're truly measuring is capacitance. So as these sensors deflect, there's a change in capacitance. And since all of the flow channels are calibrated, we then convert that to pressure, which we then convert to shear stress. So just to emphasize, that fact. Okay, so the data we're going to talk about today, we looked at a polymer system which consisted of nylon 6,6, which is a semi-crystalline polyamide, and we put this into formic acid solution. And I just have an image here on the left showing you the polymers, the nylon 6,6 in the solid state, just giving you an idea of the size of these pellets. So they're odd shaped, sort of rhomboid pellets with dimensions roughly 3 to 5 millimeters each. And the initial sample preparation that we followed was basically a suggestion of a potential customer that we were trying to work with. When they worked with these samples using a different type of instrumentation, they would mix this, the nylon in the formic acid for 2 hours and then measure. And we were also working initially at their concentration, which was at about 110 milligrams per milliliter. Ultimately, we were interested in doing a serial dilution of the stock so that we could get a concentration variation in viscosity for this polymer. And then we could do some analysis, which we'll go over at the end. So we ultimately looked at between 10 and 110 milligrams per milliliter. So starting with the stock solution, with that initial preparation, with the relatively limited time of mixing, what we're going to look at here is shear rate sweeps. And we are using, in this case, our automated VROC initium with the flow channel, which we describe as B05. So what that coding just means it corresponds to the channel depth, the flow channel depth, and then the maximum pressure that can be handled by the flow channel. So the channel depth is 50 microns, max pressure 40 kilopascals. And our testing parameters, we operated at 25 C, and we did a shear rate sweep from about 60 to about 1,000 inverse seconds. And so if we look at the data on the right in the plot, we have viscosity and centipoise as a function of shear rate. And we prepared two separate samples of the same concentration within some error. And what we see is viscosity looks like it is increasing with shear rate. And there's some slight variation between the two samples, but the general trend is there. And so this is quite unusual, viscosity increasing with shear rate, referred to as shear thickening. It does happen, but it's not something that happens as commonly as, say, shear thinning. So to me, this is something that I wanted to look into in some more detail. And then also factor in that we're looking at basically a homopolymer at moderate concentrations at low to moderate shear rates. There's nothing extreme here, so it seemed like it would be a good idea to look at more detail as to what's happening in the system. So I took the data at a shear rate of close to about 120 inverse seconds, which is I've highlighted here with the circle. And so let me just point out now that in addition to this average viscosity value, which the software puts out for you, there's a lot of detailed information that's also constantly being put onto the screen when you're doing the measurement, and then you have access to once the measurement is done, and you can go in and you can look at the details of what's happening. So we're going to look at that particular set of data to see what we can find out about this situation. So what we're going to look at is transient behavior in the viscosity and the pressure. So transient just corresponds to viscosity as a function of time. And so that's what we're looking at here on the left plot. We have viscosity again in centipoise as a function of time at this particular shear rate, which was close to 120 inverse seconds. So what we see is that there's viscosity overshoot prior to finally reaching what looks like a plateau in the viscosity. This is unusual. This is not typical behavior of even a polymer system. And so then if we look a little closer, because what we also have, remember, we're ultimately using pressure drop across the flow channel to do all of our calculations. So if we now look at how this pressure profile changes as a function of time, this is going to provide even more information. So what these X points on the transient viscosity data correspond to the times where I'm pulling up the pressure drop across the flow channel. So what we see at the early times, things are starting off looking, reasonably well behaved, like things are, uniform flow. We're on the road to fully developed flow, uniform sample, everything looks reasonable. And then we start to see this drift here, where there's basically an overall pressure buildup in the system and we lose linearity. So remember at the beginning when we were talking about the VROC technology, the idea is that if everything's going smoothly and as expected, your pressure drop across the flow channel will be linear with an R² value close to 1. And we see that we start to deviate from that as time goes on and we're pumping more of the polymer solution through the flow channel. So what this is telling us is then that we're violating some of our assumptions. It's not immediately clear yet what's happening. We can speculate, and we will a little later on. But so this leads us to start questioning what's happening, and if the fact that we start seeing this improper pressure drop across the flow channel, this overshoot. It leads us to believe that there's some inhomogeneities in the flow channel as the sample's flowing along, and we're not getting a consistently developed profile along the length of the channel. So let's think about how we prepped our samples. So we have these polymers that start in the solid state, and we have to consider, the dissolution process when we're thinking about how we prep these. So if you think of just when you make a solution, a salt solution, a sugar solution, these are small molecules in with the molecules positioned on a lattice, and they dissolve, if not instantaneously, quite quickly. Within a few minutes, it's clear that everything has gone into solution, particularly if you add some mixing or agitation. However, when you consider polymers, these have a much higher molecular weight, and the dissolution now is going to be a multi-step process. So unlike the simple sugars or salts that just have to release from the lattice structure that they're in and go into solution, now you have, if you want to look at this image we have of the solid state polymer, now you have this dense, entangled, and in our case with the nylon 6,6, since it's semi-crystalline, there's going to likely be some even denser regions of crystallinity. So now you have to have solvent diffuse into this solid, tightly packed polymer, and then this has to, over time, induce chain disentanglement. And so I've sort of broken this down into a couple steps with the pictures, but obviously your initial state is this solid polymer, and so remember the picture of the pellets and the length scale that those were on, so that's 3 to 5 millimeters. So that you start with this solid state, densely packed, some crystalline regions in our case, and then ultimately what you're trying to get to is individual solvated polymers in solution. And so I've sort of drawn, one of the potential middle steps where you have basically some swollen gel-like particles. So you sort of started to break apart the bigger solid structure. They started to swell, but they're not yet individual solvated polymers. And of course, this is going to be a continuum until you reach the final state. And so you're going to have a distribution of these, what I call gel particles, distribution of sizes, and then ultimately you'll have a mixture of these and individual polymers. So I just wanted to emphasize, as we got this data and it wasn't, making sense, it really, caused us to go look at our system and what was happening and how we were prepping it. And just to also add in there, when you're thinking about how long will the dissolution process take for a given polymer, you can also sort of look at solubility parameters, which you can look up. They're available in the literature or, say, the Polymer Handbook. And so if you look at those for nylon 6,6 and formic acid, they're reasonably close, and it's quite common to use formic acid as a solvent for nylon, but they're not exactly equivalent. And so, maybe that slight differential then also impacts timing. And as I mentioned, the fact that this is semi-crystalline and those regions are more dense, then that can also introduce a little more or lengthy time dependence on the dissolution process. So, and when we were initially starting these experiments, as I mentioned, we were sort of talking to a potential customer who was saying how they worked with these systems. But then after we started seeing the data and questioning the situation, if you go look in the literature, either there are ASTMs for preparation of nylon and formic acid, and then there's a variety of academic publications on the same system. It can vary. The recommendations for how to prep these samples can vary quite a bit, from, say, 2 hours of mixing to mix until visibly in solution to strictly mixing for at least 1 week period. And I will mention that, ultimately, as you can guess, we continued mixing these formulations and then tested them again. And I will say that visibly, just from the naked eye, I could not see any difference between what happened after 2 hours and what happened after a week. So it's important that you can't necessarily go by just visuals alone. Okay, so now that we sort of thought about our samples and considered other preparation options based on literature and just the whole polymer dissolution process, we continued to mix this solution. So it was continuously on a slow rotating mixer for a week-long period. And again, we're still looking at the stock solution. And now what we see when we look at viscosity as a function of shear rate, I've included the previous data just for comparison, but now on the or the sample that was mixed for a much longer period of time and mixed continuously now shows Newtonian behavior. So shear rate independent viscosity over the range that we tested for this sample, which was about 120 to 1,000 inverse seconds. So clearly, something has changed about the sample. So again, remembering that we have a lot more information than just this average viscosity value as a function of shear rate. We pull out the transient behavior. I didn't mark it clearly in this instance, but we're looking at the same shear rate that we looked at for the initial sample, the initial shorter mixing sample. So this is at 120 inverse seconds. So now we have the viscosity as a function of time for the same shear rate that we looked at before. And what we now see is very standard behavior when you're looking at viscosity as a function of time. So we see a continuous increase until it reaches a plateau, and then we see a steady plateau with some noise. And this is the typical behavior when things are, going as expected. So you have to initiate the flow, and then it takes a short period of time for the profile to fully develop and reach a steady state. And so then if we look at the pressure drop along the flow channel, as we did before, again, I've marked the time points that we pull up the profiles. We see that there's a gradual increase with time, and the profiles remain linear and stable in the plateau region. So again, this is indicating that things are flowing uniformly, fully developed steady state profiles as expected. So if we want to just compare, side by side some of the details of the system. So here we're just going to look at the pressure profiles for the 2 hours versus the 1 week of mixing. And so this is again just pressure versus sensor position. On the left we have the sample that was only mixed for 2 hours, and on the right we have the one that we mixed for an entire week. And what we see is that for the one on the left, as we've already stated, the one on the right, this is typical behavior when nothing is going wrong or nothing unexpected is happening. And on the left is where we see that unusual behavior, which we believe is due to the presence of non-fully solvated polymers. So it's not the case where we have individual polymers fully solvated in the solution, but we're in some middle state where we have probably some spectrum of individual polymers and then gel-like particles. And what we see there in this state is that there's an overall pressure buildup in the flow channel. So the pressure, max pressure, gets higher than it does in the 1 week mixed state. So this overall pressure buildup, which then is more exaggerated towards the exit of the flow channel. So although we can't, because we don't have flow visualization techniques, so we can't formally come to a conclusion. You could probably speculate a variety of ways, but it seems that some of these, there's a potential inhomogeneity in the system as you move through the channel, causing this pressure buildup. And it's most pronounced. So what I should have done here is also brought back what looked like shear thickening, because the deviations from expected behavior are most pronounced at the low flow rate. But if we get to the higher flow rates, let's just jump back for a second. When we get to the higher flow rates, the behavior becomes more normal. So, in theory, potential, these higher flow rates then force this buildup out that might artificially bump up the pressure. So it's speculation, as I said, because we can't visualize the flow field in any way. But what we do know is that when we adjust how we prepare our sample and do something more rigorous, more extensive to ensure that it is fully solvated and homogeneous, then we eliminate this measurement artifact and we're able to get consistent data without any red flags. So moving forward then with that particular sample preparation protocol, so now everything that we worked with, we allow to mix for an extended period of time, and we're very observant about how the transient behavior is playing out, and we're watching that to make sure everything looks what I'll call normal. So now we get the viscosity as a function of shear rate for our concentration series. So if you remember, we were going from what is down to about 11 up to 110, which is our stock solution. And then we have formic acid as a reference fluid. And so what we can see is over the range that we test, and we have a slightly different test range for each sample because of we can access a different range in shear rates using a single chip based on the change in viscosity. So that's why they shift a bit. But what we see is they're Newtonian over the range that we tested. And there's no unusual shear thickening behavior that truly exists in the system for these extensively solvated samples. And because it's Newtonian over this range, we can easily translate this to relative viscosity as a function of concentration. And the reason we do this is because there's sort of a simple, straightforward analysis that we can do to extract the molecular weight from this data. Because we didn't know what the molecular weight was ahead of time. So that was a benefit of this measurement. So if we then focus in on our viscosity as a function of concentration and think about, so when we were doing this, we didn't think ahead necessarily to do concentrations low enough to do a formal intrinsic viscosity analysis. There wasn't quite enough data in that region, but there are different models for different concentration regimes in polymer solutions. So depending on the concentration, viscosity is going to scale differently. And so there's empirical evidence of this. So as you are obviously in the limit of infinite dilution, you have the individual chains. And then as you move up in concentrations, ultimately as you pack more and more polymers into the system, chains will overlap. And then ultimately at high enough concentrations and at high enough molecular weights, you can have chain entanglement. So there's an equation, the Martin equation, that can be used in basically sort of this mid-range, what I'll refer to as semi-dilute. And this isn't extremely rigorously defined. It's more, beyond the limit of infinite dilution, starting into the area of chain overlap, but certainly well below the concentration where you would have chain entanglement. So it's this mid-range, loosely defined as the semi-dilute range. And so that's this equation given here, which has an exponential form. This is just the viscosity of the polymer solution divided by the viscosity of the solvent, in this case the formic acid. C is just polymer concentration. And then this here is just, as it's probably familiar to many people, is the intrinsic viscosity parameter, and K sub m is just another parameter for the fit in the exponential term. So if we adjust this equation to get the reduced viscosity, which is what we plot here, the reduced viscosity versus concentration, we can easily fit an exponential curve to a portion of the data to extract. We're really only interested in the intrinsic viscosity to get the molecular weight. So we fit it over this mid-range concentrations, and I found that if I narrowed the range and only fit the first few points, the data quality or the fit quality did not improve. But then if I went beyond the 60 milligrams per milliliter, then the quality of the fit dropped drastically. So this seemed to be the appropriate range for this set of data. So from that, we could get the intrinsic viscosity, which is in the table here and is clear from the model fit on the plot. So now what we do is we take that value, and because the nylon 6,6 and formic acid has been studied somewhat extensively, you can easily find values for the equation that relates the intrinsic viscosity to the viscosity average molecular weight. So what I'm looking for is this prefactor here, K or kappa, and this exponent, power law exponent A. And so I did find values for these. I found them in both some publications, and then they're also in the Polymer handbook. And I found somewhat consistent values across the resources. And so using the intrinsic viscosity and the parameters that I found in the literature, I was able to estimate this viscosity average molecular weight for our polymer system, which I found here to be slightly less than 30,000. So that sort of concludes the data presentation. And I just wanted to summarize and point out that it's really important to, when you get viscosity data, don't just look at, unless you're dealing with some sort of quality control environment and you test the same thing over and over again, and it's no opportunity for unusual behavior, that's kind of an isolated case. But it's very important to look at your data and critically review what's happening there, because this type of measurement is prone to artifacts because it is a calculated property. And in this case, looking closely at the data and then thinking about our system and what was happening, it basically guided us to question how we were preparing our polymer samples and then to properly prepare them in the end. And this avoided any sort of data misinterpretation, which can happen, because it's quite interesting if you prepare a shear thickening fluid that's unique, right? But you want to avoid this misinterpretation. And then ultimately, we were able to, once we reevaluated the situation, we were ultimately able to obtain quality data that we could analyze and get some useful parameters. So that concludes everything I wanted to cover. And so now we can open it up for any questions. And then, as always, sometimes it can take a while to come up with questions. So if you don't think of any questions right now, you can always, you'll get the webinar sent to you, and you can always contact us later, and we'll be happy to talk to you about anything that you'd like to ask. Okay, so it looks like we're not getting anything coming in, so we'll end it here. Thank you for joining us for our first webinar this year. And as stated, if you think of something later you want to contact us about, please do. We'd be happy to get back to you and help you, understand viscosity. Okay, great. Thank you very much.